human understanding of the cosmos. Of all nature's elements, of all the different types of atoms that can create patterns in a star's spectrum, astrophysicists recognize and use one in particular to find the ages of the youngest stars. That element is lithium, the third simplest and lightest in the periodic table, and familiar to some on Earth as the active ingredient of some antidepressant medications. In the periodic table of the elements, lithium occupies the position immediately after hydrogen and helium, which are deservedly far more famous because they exist in immensely greater amounts throughout the cosmos. During its first few minutes, the universe fused hydrogen into helium nuclei in great numbers, but made only relatively tiny amounts of any heavier nucleus. As a result, lithium remained a rather rare element, distinguished among astrophysicists by the cosmic fact that stars hardly ever make more lithium, but only destroy it. Lithium rides down a one-way street because every star has more effective nuclear fusion reactions to destroy lithium than to create it. As a result, the cosmic supply of lithium has steadily decreased and continues to do so. If you want some, now would be a good time to acquire it. For astrophysicists, this simple fact about lithium makes it a highly useful tool for measuring the ages of stars. All stars begin their lives with their fair and proportionate share of lithium, left behind by the nuclear fusion that occurred during the universe's first half hour, and during the Big Bang itself. And what is that fair share? About 1 in every 100 billion nuclei. After a newborn star begins its life with this richness of lithium, things go downhill, lithium-wise, as nuclear reactions within the star's core slowly consume lithium nuclei. The steady and sometimes episodic mixing of matter in the core with matter outside carries material outward, so that after thousands of years, the star's outer layers can reflect what previously happened in its core. When astrophysicists look for the youngest stars, they therefore follow a simple rule: look for the stars with the greatest abundance of lithium. Each star's number of lithium nuclei in proportion to, for example, hydrogen, will locate the star at some point along a graph that shows how stars' ages correlate with lithium in their outer layers. By using this method, astrophysicists can identify, with confidence, the youngest stars in a cluster, and can assign each of those stars a lithium-based age. Because stars are efficient destroyers of lithium, older stars show little if any of the stuff. Hence the method works well only for stars less than few hundred million years old. But for these younger stars, the lithium approach works wonders. A recent study of 24 young stars in the Orion Nebula, all of which have masses close to the Sun's, show ages that range between 1 and 10 million years. Someday astrophysicists may well identify still younger stars, but for now, 1 million years represents about the best they can do. Except for dispersing the cocoons of gas from which they formed, groups of newborn stars bother nobody for a long time, as they quietly fuse hydrogen into helium in their cores and destroy their lithium nuclei as part of their fusion reactions. But nothing lasts forever. Over many million years, in response to the continual gravitational perturbations from enormous clouds that pass by, most would-be star clusters evaporate, as its members scatter into the general pool of stars in the galaxy. Nearly 5 billion years after our star formed, the identity of the Sun's siblings has vanished, whether or not those stars remain alive. Of all the stars in the Milky Way and other galaxies, those with low masses consume their fuel so slowly that they live practically forever. Intermediate mass stars such as our Sun eventually turn into red giants, expanding their outer gas layers 100-fold in size as they slide toward death. These outer layers become so tenuously connected to the star that they drift into space, exposing a core of spent nuclear fuels that powered the star's 10 billion-year lives. The gas that returns to space will be swept up by passing clouds, to participate in later rounds of star formation. Despite their rarity, the highest mass stars hold nearly all the evolutionary cards. Their high masses give them the greatest stellar luminosities, some of them can boast 1,000,000 times the Sun's, and because they consume their nuclear fuel far more rapidly than low-mass stars do, they have the shortest lives of all stars, only a few million years, or even less. Continued thermonuclear fusion within high-mass stars allows them to manufacture dozens of elements in their cores, starting with hydrogen and proceeding to helium, carbon, nitrogen, oxygen, neon, magnesium, silicon, calcium, and so on, all the way to iron. These stars forge still more elements in their final fires, which can briefly outshine a star's entire home galaxy. Astrophysicists call each of these outbursts a supernova, similar in appearance to the Type Ia supernovae described in Chapter 5. A supernova's explosive energy spreads both the previously made and the freshly minted elements through the galaxy, blowing holes in its distribution of gas and enriching nearby clouds with the raw materials to make new dust grains. The blast moves supersonically through these interstellar clouds, compressing their gas and dust, possibly creating some of the high-density pockets needed to form stars. The greatest gift to the cosmos from these supernovae consists of all the elements other than hydrogen and helium, elements capable of forming planets and protists and people. We on Earth live on the product of countless stars that exploded billions of years ago, in epochs of Milky Way history long before our Sun and its planets. Condensing within the dark and dusty recesses of an interstellar cloud, itself endowed with chemical enrichment furnished from previous generations of high-mass stars. How did we come to taste this delicious kernel of knowledge? The fact that all the elements beyond helium were forged within stars? The author's award for the most underappreciated scientific discovery of the 20th century goes to the recognition that supernovae, the explosive death throes of high-mass stars, provide the primary source for the origin and abundances of heavy elements in the universe. This relatively unsung realization appeared in a lengthy research article, published in 1957 in the U.S. Journal Reviews of Modern Physics under the title, The Synthesis of the Elements in Stars, and written by Margaret Burbidge, Jeffrey R. Burbidge, William Fowler, and Fred Hoyle. In this paper, the four scientists created a theoretical and computational framework that freshly interpreted and melded together 40 years of musings by other scientists on two key topics: the sources of stellar energy and the transmutation of chemical elements. Cosmic nuclear chemistry, the quest to understand how nuclear fusion makes and destroys different types of nuclei, has always been a messy business. The crucial questions have always included: how do the various elements behave when various temperatures and pressures act upon them? Do the elements fuse or do they split? How easily do they do this? Do these processes liberate new kinetic energy or absorb existing kinetic energy? And how do the processes differ for each element in the periodic table? What does the periodic table of the elements mean to you? If you are like most former students, you will remember a giant chart on the wall of your science class, tricked out with mysterious boxes in which cryptic letters and symbols murmured tales of dusty laboratories to be avoided by young souls in transition. But to those who know its secrets, this chart tells 100 stories of cosmic violence that brought its components into existence. The periodic table lists every known element in the universe, arranged by the increasing number of protons in each element's nuclei. The two lightest elements are hydrogen, with 1 proton per nucleus, and helium, with 2. As the four authors of the 1957 paper saw, under the right conditions of temperature, density, and pressure, a star can use hydrogen and helium to create all the other elements in the periodic table. The details of this creation process, and of other interactions that destroy nuclei rather than create them, provide the subject matter for nuclear chemistry, which involves the calculation and use of collision cross-sections, to measure how closely one particle must approach another before they are likely to interact significantly. Physicists can easily calculate collision cross-sections for cement mixers, or double-wide mobile homes moving down the street on flatbed trucks, but they face greater challenges in analyzing the behavior of tiny, elusive subatomic particles. A detailed understanding of collision cross-sections enables physicists to predict nuclear reaction rates and pathways. Often small uncertainties in their tables of cross-sections lead them into wildly erroneous conclusions. Their difficulties resemble what would happen if you tried to navigate your way through one city's subway system with another city's subway map as your guide. Your basic theory would be correct, but the details could kill you. Despite their ignorance of accurate collision cross-sections, scientists during the first half of the 20th century had long suspected that if exotic nuclear processes exist anywhere in the universe, the centers of stars seemed likely places to find them. In 1920, the British theoretical astrophysicist Sir Arthur Eddington published a paper entitled The Internal Constitution of the Stars, in which he argued that the Cavendish Laboratory in England, the leading center for atomic and nuclear physics research, could not be the only place in the universe that managed to change some elements into others. But is it possible to admit that such a transmutation is occurring? It is difficult to assert, but perhaps more difficult to deny, that this is going on. And what is possible in the Cavendish Laboratory may not be too difficult in the Sun. I think that the suspicion has been generally entertained that the stars are the crucibles in which the lighter atoms which abound in the nebulae are compounded into more complex elements. Eddington's paper, which foreshadowed the detailed research of Burbage, Fowler, and Hoyle, appeared several years before the discovery of quantum mechanics, without which our understanding of the physics of atoms and nuclei must be judged feeble at best. With remarkable prescience, Eddington began to formulate a scenario for star-generated energy via the thermonuclear fusion of hydrogen to helium and beyond. We need not bind ourselves to the formation of helium from hydrogen as the sole reaction which supplies the energy, although it would seem that the further stages in building up the elements involve much less liberation, and sometimes even absorption, of energy. The position may be summarized in these terms. The atoms of all elements are built of hydrogen atoms bound together, and presumably have at one time been formed from hydrogen. The interior of a star seems as likely a place as any for the evolution to have occurred. Any model of the transmutation of the elements ought to explain the observed mix of elements found on Earth and elsewhere in the universe. To do this, physicists needed to find the fundamental process with which stars generate energy by turning one element into another. By 1931, with theories of quantum mechanics rather well developed, the British astrophysicist Robert D. Escourt Atkinson published an extensive paper, summarized as a synthesis theory of stellar energy and of the origin of the elements, in which the various chemical elements are built up step by step from the lighter ones in stellar interiors, by the successive incorporation of protons and electrons one at a time. In the same year, the American nuclear chemist William D. Harkins published a paper noting that elements of low atomic weight are more abundant than those of high atomic weight and that, on the average, the elements with even atomic numbers are about 10 times more abundant than those with odd atomic numbers of similar value. Harkins surmised that the relative abundances of the elements depend on nuclear fusion rather than on chemical processes such as combustion, and that the heavy elements must have been synthesized from the light ones. The detailed mechanism of nuclear fusion in stars could ultimately explain the cosmic presence of many elements, especially those that you will obtain each time you add the 2-proton, 2-neutron helium nucleus to your previously forged element. These constitute the abundant elements with even atomic numbers that Harkins described. But the existence and relative numbers of many other elements remained unexplained. Some other means of element buildup must have been at work in the cosmos. The neutron, discovered in 1932 by the British physicist James Chadwick while working at the Cavendish Laboratories, plays a significant role in nuclear fusion that Eddington could not have imagined. To assemble protons requires hard work, because protons naturally repel one another, as do all particles with the same sign of electric charge. To fuse protons, you must bring them sufficiently close to overcome their mutual repulsion for the strong nuclear force to bind them together. The chargeless neutron, however, repels no other particle, so it can simply march into somebody else's nucleus and join the other assembled particles, held there by the same force that binds the protons. This step does not create another element, which is defined by a different number of protons in each nucleus. By adding a neutron, we make an isotope of the nucleus of the original element, which differs only in detail from the original nucleus because its total electric charge remains unchanged. For some elements, the freshly captured neutron proves to be unstable once it joins the nucleus. In that case, the neutron spontaneously converts itself into a proton and an electron. In this way, like the Greek soldiers who breached the walls of Troy by hiding inside a wooden horse, protons can sneak into a nucleus in the guise of neutrons. If the ongoing flow of neutrons stays high, each nucleus can absorb many neutrons before the first one decays. These rapidly absorbed neutrons help to create an ensemble of elements whose origin is identified with the rapid neutron capture process, and differ from the assortment of elements that result when neutrons are captured slowly, where each successive neutron decays into a proton before the nucleus captures the next one. Both the rapid and the slow neutron capture processes are responsible for creating many of the elements not otherwise formed through traditional thermonuclear fusion. The remaining elements in nature can be made by a few other processes, including slamming high-energy photons into the nuclei of heavy atoms, which then break apart into smaller ones. Generating and releasing the energy in its interior, it allows the star to support itself against gravity. Without its production of energy through thermonuclear fusion, each stellar ball of gas would simply collapse under its own weight. This fate weighs on stars that exhaust their supplies of hydrogen nuclei in their cores. As already noted, after converting its hydrogen into helium, the core of a massive star will next fuse helium into carbon, then carbon to oxygen, oxygen to neon, and so forth up to iron. To successively fuse this sequence of heavier and heavier elements requires successively higher temperatures for the nuclei to overcome their natural repulsion. Fortunately, this happens all by itself, because at the end of each intermediate stage, when the star's energy source temporarily shuts off, the inner regions collapse, the temperature rises, and the next pathway of fusion kicks in. Since nothing lasts forever, the star eventually confronts one enormous problem. The fusion of iron does not release energy, but instead absorbs it. This brings bad news to the star, which can now no longer support itself against gravity by pulling a new energy-releasing process out of its nuclear fusion hat. At this point, the star suddenly collapses, forcing its internal temperature to rise so rapidly that a gigantic explosion ensues as the star blows its guts to smithereens. Throughout each explosion, the availability of neutrons, protons, and energy allows the supernova to create elements in many different ways. In their 1957 article, Burbage, Fowler, and Hoyle combined the well-tested tenets of quantum mechanics, the physics of explosions, the latest collision cross-sections, the varied processes that transmute elements into one another, and the basics of stellar evolutionary theory to implicate supernova explosions decisively as the primary source of all the elements heavier than hydrogen and helium in the universe. With high-mass stars as the source of heavy elements, and supernovae as the smoking gun of element distribution, the Fab Four acquired the solution to one other problem for free: when you forge elements heavier than hydrogen and helium in stellar cores, you do the rest of the universe no good unless you somehow cast those elements forth into interstellar space, making them available to form worlds with wombats. Burbage, Fowler, and Hoyle unified our understanding of nuclear fusion in stars with the element production visible throughout the universe. Their conclusions have survived decades of skeptical analysis, so their publication stands as a turning point in our knowledge of how the universe works. Yes, Earth and all its life comes from stardust. No, we have not solved all of our cosmic chemical questions. A curious contemporary mystery involves the element technetium, which, in 1937, was the first element to be created artificially in Earth-bound laboratories. We have yet to discover technetium on Earth, but astronomers have found it in the atmospheres of a small fraction of the red giant stars in our galaxy. This would hardly surprise us, were it not for the fact that technetium decays to form other elements, and does so with a half-life of a mere 2 million years, far shorter than the age and life expectancy of the stars in which we observe it. This conundrum has led to exotic theories that have yet to achieve consensus within the community of astrophysicists. Red giants with these peculiar chemical properties are rare, but sufficiently nettlesome for a cadre of astrophysicists who specialize in the subject to generate and distribute the newsletter of chemically peculiar red giant stars. Not available on most newsstands, this publication typically contains conference news and updates on research still in progress. To interested scientists, these ongoing chemical mysteries have an allure as strong as the questions related to black holes, quasars, and the early universe. But you hardly ever read about them. Why? Because, quite typically, the media has predetermined what deserves coverage and what does not. Apparently, the news about the cosmic origins of every element in your body and your planet doesn't make the cut. Here is your chance to redress the wrongs that contemporary society has inflicted upon you. Let's take a journey through the periodic table, pausing here and there to note the most intriguing facts about the various elements, and to admire how the cosmos made them all from the hydrogen and helium that emerged from the Big Bang. The Elemental Zoo. The periodic table of the elements, lovingly created by chemists and physicists during the past 2 centuries, embodies organizing principles that explain the chemical behavior of all the elements that we know in the universe, or may someday discover. For this reason, we ought to regard the periodic table as a cultural icon, an exemplar of our society's ability to organize its knowledge. The table testifies to the enterprise of science as an international human adventure, conducted not only in laboratories but also in particle accelerators, and at the space and time frontiers of the entire cosmos. Amid this well-merited respect, every now and then an entry in the periodic table will strike even a grown-up scientist as a strange beast in a zoo of one-of-a-kind animals conceived and executed by Dr. Seuss. How else can we believe that sodium is a deadly, reactive metal that you can cut with a butter knife, and that pure chlorine is an evil-smelling, deadly gas, yet when we combine sodium and chlorine, we make sodium chloride, a harmless compound essential to life. Better known as table salt? What about hydrogen and oxygen, 2 of the most abundant elements on Earth and in the universe? One is an explosive gas, while the other promotes violent combustion, yet adding the 2 produces liquid water, which puts out fires. Amid all the chemical interactions in the periodic table's little shop of possibilities, we find the elements most significant to the cosmos. These offer the chance to view the table through the lens of an astrophysicist. We shall grasp that chance and dance our way across the table, saluting its most distinguished entries and admiring its little oddities. The periodic table emphasizes the fact that each of nature's elements distinguishes itself from all others by its atomic number, the number of protons in each nucleus of that element. Complete atoms always have a number of electrons orbiting the nucleus equal to the element's atomic number, so the total atom has 0 electric charge. Different isotopes of a particular element have the same number of protons and electrons, but different numbers of neutrons. Hydrogen, with only 1 proton in each nucleus, is the lightest and simplest element, made entirely during the first few minutes after the Big Bang. Out of the 94 naturally occurring elements, hydrogen claims more than 2/3 of all the atoms in human bodies and more than 90% of all the atoms in the cosmos, including the Sun and its giant planets. The hydrogen inside the core of the Sun's most massive planet, Jupiter, feels so much pressure from the overlying layers that it behaves more like an electromagnetically conductive metal than a gas, and helps to create the strongest magnetic field among the Sun's planets. The English chemist Henry Cavendish discovered hydrogen in 1766 while experimenting with H2O. Hydrogenes is the Greek word for water forming. Whose gen appears in such English words as genetic, though his fame among astronomers rests on his having been the first person to calculate Earth's mass accurately by measuring the gravitational constant g that appears in Newton's famous equation for gravity. Every second of every day and night, 5 billion tons of fast-moving hydrogen nuclei slam together to make helium nuclei within the Sun's 15 million degree core. About 1% of the mass involved in this fusion transforms itself into energy, leaving the other 99% in the form of helium. Helium, the second most abundant element in the universe, can be found on Earth only in a few underground pockets that trap this gas. Most of us know only helium's whimsical side, available for testing through over-the-counter purchases. When you inhale helium, its low density in comparison with atmospheric gases increases the vibrational frequency within your windpipe, causing you to sound like Mickey Mouse. The cosmos contains 4 times more helium than all other elements combined. One of the pillars of Big Bang cosmology is the prediction that throughout the cosmos, no fewer than about 8% of all atoms are helium, which the well-mixed primeval fireball manufactured during its immediate post-birth pangs. Since the thermonuclear fusion of hydrogen within stars produces additional helium, some regions of the cosmos can accumulate more than their initial 8% share of helium, but, just as the Big Bang model predicts, no one has ever found a region of our galaxy or anybody else's galaxy with less. Some 30 years before they discovered an isolated helium on Earth, astrophysicists had detected helium in the Sun by the telltale features that they saw in the Sun's spectrum of light during the total eclipse of 1868. They naturally named this previously unknown material helium after Helios, the Greek sun god. With 92% of hydrogen's buoyancy in air, but without the explosive characteristics of hydrogen that destroyed the German Hindenburg dirigible, helium provides the gas of choice for the outsized balloon characters of the Macy's Thanksgiving Day Parade, making the famed department store second only to the U.S. military as the world's top consumer of helium. Lithium, the third simplest element in the universe, has 3 protons in each nucleus. Like hydrogen and helium, lithium was made soon after the Big Bang, but unlike helium, which is often made in subsequent nuclear reactions, lithium will be destroyed by every nuclear reaction that occurs in stars. Hence we expect to find no object or region with lithium present in more than the relatively small relative abundances, no more than 0.0001% of the total, produced in the early universe. As predicted by our model of element formation during the first half hour, no one has yet found a galaxy with more lithium than this upper limit. The combination of the upper limit on helium and the lower limit on lithium furnishes us with a potent dual constraint to apply in testing the theory of Big Bang cosmology. A similar test of the Big Bang model of the universe, which it has passed with flying colors, compares the abundance of deuterium nuclei, each of which has 1 proton and 1 neutron, with the amount of ordinary hydrogen. Fusion during the first few minutes produced both of these nuclei, but made far more of simple hydrogen. Like lithium, the next 2 elements in the periodic table, beryllium and boron, owe their origin mainly to thermonuclear fusion in the early universe, and they appear only in relatively modest numbers throughout the cosmos. The scarcity on Earth of the 3 lightest elements after hydrogen and helium makes them bad news for those who accidentally ingest them, since evolution has proceeded essentially without encountering them. Intriguingly, controlled doses of lithium do seem to relieve certain types of mental illness. With carbon, element number 6, the periodic table springs into glorious efflorescence. Carbon. Atoms, with 6 protons in every nucleus, appear in more kinds of molecules than the sum of all non-carbon-containing molecules combined. The cosmic abundance of carbon nuclei, forged in the cores of stars, churned to their surfaces, and released in copious amounts into the Milky Way galaxy, joins with carbon's ease in forming chemical combinations to make carbon the best element on which to base the chemistry in diversity of life. Just edging out carbon in abundance, oxygen also offers a highly reactive and abundant element, similarly forged within and released from aging stars and stars that explode as supernovae. Both oxygen and carbon constitute major ingredients for life as we know it. The same processes made and distributed nitrogen, element number 7, which again appears in great quantities throughout the universe. But what about life as we don't know it? Could other life forms use a different element as the heart of their complex shapes? How about life based on silicon, element number 14? Silicon sits directly below carbon on the periodic table, which means that silicon can create the same sorts of chemical compounds that carbon does, with silicon taking the place of carbon. In the end, we expect carbon to prove superior to silicon, not only because carbon has 10 times the abundance of silicon in the cosmos, but also because silicon forms chemical bonds that are either substantially stronger or noticeably weaker than those that carbon makes. In particular, the strength of the bonds between silicon and oxygen makes tough rocks, whereas complex molecules based on silicon lack the hardiness to survive ecological stresses that carbon-based atoms exhibit. These facts don't stop science fiction writers from championing silicon, thus keeping exobiological speculation on its toes and allowing us to wonder what the first truly alien life form will be like. In addition to forming an active ingredient in table salt, sodium glows across this great land as hot sodium gas in most municipal street lamps. These lamps burn brighter, longer, and use less energy than conventional incandescent bulbs do. They come in 2 varieties, the common high-pressure lamps, which look yellow-white, and the rarer, low-pressure lamps, which look orange. It turns out that while all light pollution hurts astronomy, low-pressure sodium lamps inflict less harm because their contamination, much more narrowly confined in color, can be easily accounted for and removed from telescope data. In a model of town telescope cooperation, the entire city of Tucson, Arizona, the closest large municipality to the Kitt Peak National Observatory, has, by agreement with the local astronomers, converted all its streetlights to low-pressure sodium lamps, which also turn out to be more efficient and therefore save energy for the city. Aluminum provides nearly 10% of Earth's crust, yet remained unknown to the ancients and unfamiliar to our grandparents because it combines so effectively with other elements. Its isolation and identification occurred only in 1827, and aluminum did not enter common household use until the late 1960s, when tin cans and tin foil yielded to aluminum cans and aluminum foil. Because polished aluminum makes a near-perfect reflector of visible light, astronomers today coat nearly all their telescope mirrors with a thin film of aluminum atoms. Although titanium has a density 70% greater than aluminum's, it's more than twice as strong. Its strength and relative lightness make titanium, the ninth most abundant element in Earth's crust, a modern darling for many applications, such as military aircraft components, that require a light, strong metal. In most cosmic locations, oxygen atoms outnumber carbon. In stars, once every carbon atom has latched onto one of the available oxygen atoms to form carbon monoxide or carbon dioxide molecules, the leftover oxygen atoms bond with other elements, such as titanium. The spectra of the light from red giant stars are riddled with features created by titanium oxide, which itself is no stranger to stars on Earth. Star sapphires and rubies owe their radiant asterisms to titanium oxide impurities within their crystal lattices, with aluminum oxide impurities adding extra color. Furthermore, the white paint used for telescope domes features titanium oxide, which happens to radiate infrared with high efficiency, a fact that greatly reduces the daytime heat accumulated within the dome. At nightfall, with the dome open, the air temperature near the telescope falls more rapidly to the temperature of the nighttime air, reducing atmospheric refraction and allowing the light from stars and other cosmic objects to arrive with greater sharpness and clarity. Although not directly named for a cosmic object, titanium derives its handle from the Titans of Greek mythology, as does Titan, Saturn's largest moon. Carbon may be the most significant element in life, but by many measures, iron, element number 26, ranks as the most important of all the elements in the universe. Massive stars manufacture elements in their core, marching through the periodic table in the sequence of increasing number of protons per nucleus, from helium to carbon to oxygen to neon, and so forward all the way to iron. With 26 protons and at least as many neutrons in its nucleus, iron has a distinctive quality that derives from the quantum mechanics rules that govern how protons and neutrons interact. Iron nuclei have the highest binding energy per nuclear particle. This means something quite simple. If you seek to split iron nuclei, you must provide them with additional energy. On the other hand, if you combine iron atoms, they will also absorb energy. It takes energy to fuse iron nuclei and it takes energy to split them apart. For all other elements, only one or the other half of this dual description applies. Stars, however, are in the business of using E equals mc squared to turn mass into energy, which they must do to oppose their tendency to collapse under their own gravity. When stars fuse nuclei in their cores, nature demands, and obtains, nuclear fusion that releases energy. By the time that a massive star fuses most of the nuclei in its core into iron, it has exhausted all its options for using thermonuclear fusion to generate energy, because any further fusion will require rather than release energy. Deprived of a source of energy from thermonuclear fusion, the star's core will collapse under its own weight, then instantly rebound in a titanic explosion known as a supernova, outshining a billion suns for more than a week. Such supernovae occur because of the special property of iron nuclei, their refusal either to fuse or to split without an input of energy. By describing hydrogen, helium, lithium, beryllium, and boron, carbon, nitrogen, and oxygen, and aluminum, titanium, and iron, we have surveyed nearly all of the key elements that make the cosmos, and life on Earth, go round. Simply for the cosmic hell of it, let's have a quick look at some far more obscure entries on the periodic table. You will almost certainly never own any significant quantities of these elements, but scientists find them not only intriguing riffs on nature's bounty but also highly useful in special circumstances. Consider, for example, the soft metal gallium. Gallium has such a low melting point that the heat from your hand will make it liquefy. Apart from this parlor demo opportunity, gallium provides astrophysicists with the active ingredient in gallium chloride, a variant on table salt that proves valuable in experiments that detect neutrinos from the sun's core. To capture these elusive neutrinos, astrophysicists create a 100-ton vat of liquid gallium chloride and set it deep underground, then watch it carefully for the results of any collisions between the neutrinos and the gallium nuclei, which turn the nuclei into germanium nuclei, each of which has 32 protons. Every transformation of gallium into germanium produces X-ray photons, which can be detected and measured every time that a nucleus gets slammed. By using these gallium chloride neutrino telescopes, astrophysicists resolved what they had called the solar neutrino problem, the fact that earlier types of neutrino detectors found neutrinos in smaller numbers than the theory of thermonuclear fusion in the sun's core had predicted. Every nucleus of the element technetium is radioactive, decaying after a few moments or a few million years into other types of nuclei. Not surprisingly, we find technetium nowhere on Earth except in particle accelerators, where we make it on demand. For reasons not yet fully understood, technetium lives in the atmospheres of a select subset of red giant stars. As we noted in the previous chapter, this would cause astrophysicists no alarm, except that technetium has a half-life of a mere 2 million years, far shorter than the ages and life expectancies of the stars in which we find it. This proves that the stars cannot have been born with the stuff, for if they had been, none would be left by now. Astrophysicists also lack any known mechanism to create technetium in a star's core and to have it dredge itself up to the surface where they observe it, a matter of uneasy fact that has spawned exotic explanations, still shy of consensus within the astrophysics community. Along with osmium and platinum, iridium gives us one of the 3 densest elements on the periodic table. 2 cubic feet of iridium weighs as much as a Buick, which makes it one of the world's best paperweights, able to defy all known office fans and window breezes. Iridium also gives scientists the world's most famous smoking gun. All over the world, a thin layer of iridium-rich material appears at the geological layer that marks the famous KT boundary, laid down 65 million years ago. Not coincidentally, most biologists believe that boundary also marks the time when every land species larger than a breadbox, including the legendary dinosaurs, went extinct. Iridium is rare on Earth's surface, but 10 times more common in metallic asteroids. Whatever might have been your favorite theory for destroying the dinosaurs, a 10-mile-wide killer asteroid from outer space, capable of raising a worldwide blanket of light-blocking debris before slowly raining downward several months later, now seems quite compelling. It's not clear how Albert would have felt about this, but physicists discovered a previously unknown element in the debris from the first hydrogen bomb test in the Pacific and named it Einsteinium in his honor. Armageddon might have been more suitable. While helium derives its name from the sun itself, 10 other elements in the periodic table draw their names from objects that orbit the sun. Phosphorus, which means light-bearing in Greek, was the ancient name for the planet Venus when it appeared before sunrise in the dawn sky. Selenium comes from selene, the Greek word for the moon, so named because this element was always found in association with the element tellurium, which had already been named for Earth. On January 1, 1801, the first day of the 19th century, the Italian astronomer Giuseppe Piazzi discovered a new planet orbiting the Sun within the suspiciously large gap between Mars and Jupiter. Maintaining the tradition of naming planets after Roman gods, Piazzi called the object Ceres after the goddess of harvest, which also provides the root for our word cereal. The excitement in the scientific community over Piazzi's find caused the next element to be discovered to be named cerium in its honor. 2 years later, another planet was found, orbiting the Sun within the same gap as Ceres. This object received the name Pallas, from the Roman goddess of wisdom. Like cerium before it, the next element discovered thereafter was named palladium in its honor. The naming party ended a few decades later, after dozens more of these planets were discovered in much the same location, and after closer analysis revealed that these objects are much much smaller than the smallest known planets. A new swath of real estate had come into view within the solar system, consisting of small, craggy chunks of rock and metal. Ceres and Pallas turned out to be not planets but asteroids, objects only a few hundred miles across. They live in the asteroid belt, now known to contain millions of objects, of which astronomers have catalogued and named upward of 15,000, somewhat more than the number of elements in the periodic table. The metal Mercury, which assumes a viscous liquid form at room temperature, owes its name to the speedy Roman messenger god. So too does the planet Mercury, the fastest moving of all the planets in the solar system. Thorium's name comes from Thor, the hammer and thunder-wielding Scandinavian god, who corresponds to the lightning bolt-wielding Jupiter in Roman mythology. By Jove, recent Hubble Space Telescope images of Jupiter's polar regions reveal extensive electrical discharges deep within its turbulent cloud layers. Saturn, most people's favorite planet, has no element named for it, but Uranus, Neptune, and Pluto are famously represented. The element uranium, discovered in 1789, received its name in honor of William Herschel's planet, discovered by him just 8 years earlier. All isotopes of uranium are unstable, spontaneously but slowly decaying to lighter elements, a process accompanied by the release of energy. If you can arrange to speed up the rate of decay with a chain reaction among uranium nuclei, you have the explosive energy release required for a bomb. In 1945, the United States exploded the first uranium bomb to be used in warfare, incinerating the Japanese city of Hiroshima. With 92 protons packed in each nucleus, uranium wins the prize as the largest and heaviest element to occur naturally, although trace amounts of still larger and heavier elements appear in places where uranium ore is mined. If Uranus merited an element, so did Neptune. Unlike uranium, however, which was identified soon after its planet, Neptunium was discovered in 1940 in the particle accelerator called the Berkeley cyclotron. 97 years after the German astronomer John Gall found Neptune in a spot on the sky predicted as the most likely spot by the French mathematician Joseph Le Verrier, who studied Uranus' unexplained orbital behavior and deduced the existence of a farther planet. Just as Neptune comes immediately after Uranus in the solar system, Neptunium comes right after uranium in the periodic table of the elements. Not found in nature, including plutonium, which immediately follows Neptunium in the periodic table and bears the name of Pluto, which the young astronomer Clyde Tombaugh found in 1930 on photographs taken at Arizona's Lowell Observatory. As with the discovery of Ceres 129 years earlier, excitement ran high. Pluto was the first planet discovered by an American and, in the absence of accurate observational data, was widely believed to be a planet of size and mass commensurate with those of Uranus and Neptune. As our measurements of Pluto's size improved, Pluto kept getting smaller. Our knowledge of Pluto's dimensions did not stabilize until the late 1970s, during the Voyager missions to the outer solar system. We now know that cold, icy Pluto is by far the Sun's smallest planet, with the embarrassing distinction of being smaller than the solar system's 6 largest moons. As with the asteroids, astronomers later found hundreds of other objects in similar locations, in this case in the outer solar system with orbits similar to Pluto's. These objects signal the existence of a heretofore undocumented reservoir of small icy objects, now called the Kuiper belt of comets. A purist could argue that like Ceres and Pallas, Pluto slipped into the periodic table under false pretenses. Like uranium nuclei, plutonium nuclei are radioactive. These nuclei formed the active ingredient in the atomic bomb dropped on the Japanese city of Nagasaki, just 3 days after the uranium bombing of Hiroshima, bringing a swift end to World War II. Scientists can use small quantities of plutonium, which produces energy at a modest, steady rate, to power radioisotope thermoelectric generators. For spacecraft that travel to the outer solar system, where the intensity of sunlight falls below the level usable by solar panels, 1 pound of this plutonium will generate 10 million kilowatt-hours of heat energy, sufficient to power a household light bulb for 11,000 years, or a human being for just about as long. Still drawing on their plutonium power to send messages to Earth, the 2 Voyager spacecraft launched in 1977 have now traveled far beyond Pluto's orbit. One of them, at nearly 100 times Earth's distance from the Sun, has begun to enter true interstellar space by leaving the bubble that the Sun's outflow of electrically charged particles creates. And so we end our cosmic journey through the periodic table of the chemical elements, right at the edge of the solar system. For reasons we have yet to determine, many people don't like chemicals, which may explain the perennial movement to rid foods of them. Perhaps sesquipedalian chemical names just sound dangerous. But in that case we should blame the chemists, and not the chemicals. Personally, we are quite comfortable with chemicals. Our favorite stars, as well as our best friends, are made of them. The origin of planets. When worlds were young. In our attempts to uncover the history of the cosmos, we have continually discovered that the segments most deeply shrouded in mystery are those that deal with origins, of the universe itself, of its most massive structures, and of the stars that provide most of the light in the cosmos. Each of these origin stories fills a vital role, not only in explaining how an apparently formless cosmos produced complex assemblages of different types of objects, but also in determining how and why, 14 billion years after the Big Bang, we now find ourselves alive on Earth to ask. How did this all happen? These mysteries arise in large part because during the cosmic Dark Ages, when matter was just beginning to organize itself into self-contained units such as stars and galaxies, most of this matter generated little or no detectable radiation. The Dark Ages have left us with only the barest possibilities, still imperfectly explored, for observing matter during its early stages of organization. This in turn implies that we must rely, to an uneasily large extent, on our theories of how matter ought to behave, with relatively few points at which we can check these theories against observational data. When we turn to the origin of planets, the mysteries deepen. We lack not only observations of the crucial, initial stages of planetary formation but also successful theories of how the planets began to form. To celebrate the positive, we note that the question, what made the planets, has grown considerably broader in recent years. Throughout most of the 20th century, this question centered on the Sun's family of planets. During the past decade, having discovered more than 100 exosolar planets around relatively nearby stars, astrophysicists have acquired significantly more data from which to deduce the early history of planets, and in particular to determine how these astronomically small, dark, and dense objects formed along with the stars that give them light and life. Astrophysicists may now have more data, but they have no better answers than before. Indeed, the discovery of exosolar planets, many of which move in orbits far different from those of the Sun's planets, has in many ways confused the issue, leaving the story of planet formation no closer to closure. In simple summary, we can state that no good explanation exists of how the planets began to build themselves from gas and dust, though we can easily perceive how the formation process, once well underway, made larger objects from smaller ones, and did so within a rather brief span of time. The beginnings of planet building pose a remarkably intractable problem, to the point that one of the world's experts on the subject, Scott Tremaine of Princeton University, has elucidated Tremaine's laws of planet formation. The first of these laws states that all theoretical predictions about the properties of exosolar planets are wrong, and the second that the most secure prediction about planet formation is that it can't happen. Tremaine's humor underscores the ineluctable fact that planets do exist, despite our inability to explain this astronomical enigma. More than 2 centuries ago, attempting to explain the formation of the Sun and its planets, Immanuel Kant proposed a nebular hypothesis, according to which a swirling mass of gas and dust that surrounded our star in formation condensed into clumps that became the planets. In its broad outlines, Kant's hypothesis remains the basis for modern astronomical approaches to planet formation, having triumphed over the concept, much in vogue during the first half of the 20th century, that the Sun's planets arose from a close passage of another star by the Sun. In that scenario, the gravitational forces between the stars would have drawn masses of gas from each of them, and some of this gas could then have cooled and condensed to form the planets. This hypothesis, promoted by the famed British astrophysicist James Jeans, had the defect of making planetary systems extremely rare. Because sufficiently close encounters between stars probably occur only a few times during the lifetime of an entire galaxy. Once astronomers calculated that almost all the gas pulled from the stars would evaporate rather than condense, they abandoned Jeans's hypothesis and returned to Kant's, which implies that many, if not most, stars should have planets in orbit around them. Astrophysicists now have good evidence that stars form, not one by one but by the thousands and tens of thousands, within giant clouds of gas and dust that may eventually give birth to about 1 million individual stars. One of these giant stellar nurseries has produced the Orion Nebula, the closest large star-forming region to the solar system. Within a few million years, this region will have produced hundreds of thousands of new stars, which will blow most of the nebula's remaining gas and dust into space. So that astronomers 100,000 generations from now will observe the young stars unencumbered by the remnants of their star-birthing cocoons. Astrophysicists now use radio telescopes to map the distribution of cool gas and dust in the immediate vicinities of young stars. Their maps typically show that young stars do not sail through space devoid of all surrounding matter. Instead, the stars usually have orbiting disks of matter, similar in size to the solar system, but made of hydrogen gas sprinkled throughout with dust particles. The term dust describes groups of particles that each contain several million atoms and have sizes much smaller than that of the period that ends this sentence. Many of these dust grains consist primarily of carbon atoms, linked together to form graphite. Others are mixtures of silicon and oxygen atoms, in essence tiny rocks, with mantles of ice surrounding their stony cores. The formation of these dust particles in interstellar space has its own mysteries and detailed theories, which we may skip past with the happy thought that the cosmos is dusty. To make this dust, atoms have come together by the millions. In view of the extremely low densities between the stars, the likeliest sites for this process seem to be the extended outer atmospheres of cool stars, which gently blow material into space. The production of interstellar dust particles provides an essential first step on the road to planets. This holds true not only for solid planets like our own but also for gas giant planets, typified in the Sun's family by Jupiter and Saturn. Even though these planets consist primarily of hydrogen and helium, astrophysicists have concluded from their calculations of the planet's internal structure, along with their measurements of the planet's masses, that the gas giants must have solid cores. Of Jupiter's total mass, 318 times Earth's, several dozen Earth masses reside in a solid core. Saturn, with 95 times Earth's mass, also has a solid core with 1 or 2 dozen times the mass of Earth. The Sun's 2 smaller gas giant planets, Uranus and Neptune, have proportionately larger solid cores. In these planets, with 15 and 17 times Earth's mass, respectively, the core may contain more than half of the planet's mass. For all 4 of these planets, and presumably for all of the giant planets recently discovered around other stars, the planetary cores played an essential role in the formation process. First came the core, and then came the gas, attracted by the solid core. Thus all planet formation requires that a large lump of solid matter must form first. Of the Sun's planets, Jupiter has the largest of these cores, Saturn the next largest, Neptune the next, Uranus after that, and Earth ranks 5th, just as it does in total size. The formation histories of all the planets pose a fundamental question: how does nature make dust coagulate to form clumps of matter many thousand miles across? The answer has 2 parts, one known and one unknown, with the unknown part, not surprisingly, closer to the origin. Once you form objects half a mile across, which astronomers call planetesimals, each of them will have sufficiently strong gravity to attract other such objects successfully. The mutual gravitational forces among planetesimals will build first planetary cores and then planets at a brisk pace, so that a few million years will take you from a host of clumps, each the size of a small town, to entire new worlds, ripe to acquire either a thin coat of atmospheric gases or an immensely thick one of hydrogen and helium. To astrophysicists, the transition from half-mile-wide planetesimals to planets reduces to a series of well-understood computer models that produce a wide variety of planetary details, but almost always yield inner planets that are small, rocky, and dense, as well as outer planets that are large and gaseous and rarefied. During this process, many of the planetesimals, as well as some of the larger objects that they make, find themselves flung entirely out of the solar system by gravitational interactions with still larger objects. All this works rather well on a computer, but building the half-mile-wide planetesimals in the first place still lies beyond astrophysicists' present abilities to integrate their knowledge of physics with their computer programs. Gravity can't make planetesimals, because the modest gravitational forces between small objects won't hold them together effectively. Two theoretical possibilities exist for making planetesimals from dust, neither of them highly satisfactory. One model proposes the formation of planetesimals through accretion, which occurs when dust particles collide and stick together. Accretion works well in principle, because most dust particles do stick together when they meet. This explains the origin of dust bunnies under your couch, and if you imagine superdust bunnies growing around the sun, you can, with only minimal mental effort, let them grow to become chair-sized, house-sized, block-sized, and before long the size of planetesimals. Ready for serious gravitational action. Unfortunately, unlike the production of actual bunnies, the dust bunny growth of planetesimals seems to require far too much time. Radioactive dating of unstable nuclei detected in the oldest meteorites implies that the formation of the solar system required no more than a few tens of millions of years, and quite possibly a good deal less time than that. In comparison with the current age of the planets, approximately 4.55 billion years, this amounts to a dram in the bucket, only 1% of the total span of the solar system's existence. The accretion process requires significantly longer than a few tens of millions of years to make planetesimals from dust, so unless astrophysicists have missed something important in understanding how dust accumulates to build large structures, we need another mechanism to surmount the time barriers to planetesimal formation. That other mechanism may consist of giant vortices that sweep up dust particles by the trillions, whirling them quickly toward their happy agglomeration into significantly larger objects. Because the contracting cloud of gas and dust that became the Sun and its planets apparently acquired some rotation, it soon changed its overall shape from spherical to plate-like, leaving the Sun in formation as a relatively dense contracting sphere at the center, surrounded by a highly flattened disk of material in orbit around that sphere. To this day, the orbits of the Sun's planets, which all follow the same direction and lie in nearly the same plane, testify to a disk-like distribution of the matter that built the planetesimals and planets. Within such a rotating disk, astrophysicists envision the appearance of rippling instabilities, alternating regions of greater and lesser density. The denser parts of these instabilities collect both gaseous material and dust that floats within the gas. Within a few thousand years, these instabilities become swirling vortices that can sweep large amounts of dust into relatively small volumes. This vortex model for the formation of planetesimals shows promise, though it has not yet won the hearts of those who seek explanations of how the solar system produced what young planets need. Upon detailed examination, the model provides better explanations for the cores of Jupiter and Saturn than for those of Uranus and Neptune. Because astronomers have no way to prove that the instabilities needed for the model to work actually did occur, we must refrain from passing judgment ourselves. The existence of numerous small asteroids and comets, which resemble planetesimals in their sizes and compositions, support the concept that billions of years ago, planetesimals by the millions built the planets. Let us therefore regard the formation of planetesimals as an established, if poorly understood, phenomenon that somehow bridges a key gap in our knowledge, leaving us ready to admire what happens when planetesimals collide. In this scenario, we can easily imagine that once the gas and dust surrounding the Sun had formed a few trillion planetesimals, this armada of objects collided, built larger objects, and eventually created the Sun's 4 inner planets and the cores of its 4 giant planets. We should not overlook the planet's moons, smaller objects that orbit all of the Sun's planets except the innermost, Mercury and Venus. The largest of these moons, with diameters of a few hundred to a few thousand miles, appear to fit nicely into the model that we have created, because they presumably also arose from planetesimal collisions. Moon building ceased once collisions had built the satellite worlds to their present sizes, no doubt because by that time the nearby planets, with their stronger gravity, had taken possession of most of the nearby planetesimals. We should include in this picture the hundreds of thousands of asteroids that orbit between Mars and Jupiter. The largest of these, a few hundred miles in diameter, should likewise have grown through planetesimal collisions, and then have found themselves stymied from further growth by gravitational interference from the nearby giant planet Jupiter. The smallest asteroids, less than a mile across, may represent naked planetesimals, objects that grew from dust but never collided with one another, once again thanks to Jupiter's influence, after attaining sizes ripe for gravitational interaction. For the moons that orbit the giant planets, this scenario seems to work quite well. All 4 giant planets have families of satellites that range in size from the large or extremely large down to the small or even minuscule. The smallest of these moons, less than a mile across, may again be naked planetesimals, deprived of any further collisional growth by the presence of nearby objects that had already grown much larger. In each of these 4 families of satellites, almost all of the larger moons orbit the planet in the same direction and in nearly the same plane. We can hardly refrain from explaining this result with the same cause that made the planets orbit in the same direction and nearly the same plane. Around each planet, a rotating cloud of gas and dust produced clumps of matter, which grew to planetesimal and then to moon sizes. In the inner solar system, only our Earth has a sizable moon. Mercury and Venus have none, while Mars' 2 potato-shaped moons, Phobos and Deimos, each span only a few miles, and should therefore represent the earliest stages of forming larger objects from planetesimals. Some theories assign the origin of these moons to the asteroid belt, with their present orbits around Mars the result of Mars' gravitational success in capturing these 2 former asteroids. And what of our moon, more than 2,000 miles in diameter, surpassed in size only by Titan, Ganymede, Triton, and Callisto among all the moons of the solar system? Did the moon also grow from planetesimal collisions, as the 4 inner planets did? This seemed quite a reasonable supposition until humans brought lunar rocks back to Earth for detailed examination. More than 3 decades ago, the chemical composition of the rock samples returned by the Apollo missions imposed 2 conclusions, one on either side of the possibilities for the moon's origin. On the one hand, the composition of these moon rocks resembles that of rocks on Earth so closely that the hypothesis that our satellite formed entirely apart from us no longer seems tenable. On the other hand, the moon's composition differs from Earth's just enough to prove that the moon did not entirely form from terrestrial material. But if the moon did not form apart from Earth, and was not made from Earth, how did it form? The current answer to this conundrum, amazing though it may seem on its surface, builds upon a once popular hypothesis that the moon formed as the result of a giant impact, early in the history of the solar system, that scooped material out of the Pacific Basin and flung it into space, where it coalesced to form our satellite. Under the new view, which has already gained wide acceptance as the best available explanation, the moon did form as the result of a giant object that struck Earth. But the object striking Earth was so large, about the size of Mars, that it naturally added some of its material to the matter ejected from Earth. Much of the material thrown into space by the force of the impact might have vanished from our immediate vicinity, but enough remained behind to coagulate into our familiar moon, made of Earth plus foreign matter. All of this occurred 4.5 billion years ago, during the first 100 million years after the formation of the planets began. If a Mars-sized object struck Earth in that bygone era, where is it today? The impact could hardly have knocked the object into pieces so small that we cannot observe them. Our finest telescopes can find objects in the inner solar system as small as the planetesimals that built the planets. The answer to this objection takes us to a new picture of the early solar system, one that emphasizes its violent collisional nature. The fact that planetesimals built a Mars-sized object, for example, did not guarantee that this object would endure for long. Not only did this object collide with Earth, but the good-sized pieces produced by that collision would also have continued to collide with Earth and the other inner planets, with each other, and with the moon. In other words, collisional terror reigned over the inner solar system during its first several hundred million years, and the pieces of giant objects that struck the planets as they formed themselves became part of these planets. The Mars-sized object's impact on Earth merely ranked among the largest in a reign of bombardment, an epoch of destruction that brought planetesimals and much larger objects crashing down on Earth and its neighbors. Seen from another perspective, this death-dealing bombardment simply marked the formation process's final stages. The process culminated in the solar system we see today, little changed during 4 billion years and more. One ordinary star, orbited by 8 planets, hundreds of thousands of asteroids, trillions of meteoroids, and trillions of comets, dirty snowballs that formed at dozens of times Earth's distance from the Sun. We must not forget the planet's satellites, which have moved, with few exceptions, in orbits with long-term stability ever since their birth, 6 billion years ago. Let's take a closer look at the debris that continues to orbit our Sun, capable both of bringing forth life and of destroying life on the worlds such as ours. Between the planets. From a distance, our solar system looks empty. If you enclosed it within a sphere large enough to contain the orbit of Neptune, then the Sun, together with all its planets and their moons, would occupy little more than 1/1,000,000th of all the space in that sphere. This result, however, assumes that interplanetary space is essentially empty. Viewed close up, however, the spaces between the planets turn out to contain all manner of chunky rocks, pebbles, ice balls, dust, streams of charged particles, and far-flung man-made probes. Interplanetary space is also permeated by immensely powerful gravitational and magnetic fields, invisible but nonetheless quite capable of affecting the objects in our neighborhood. These small objects and cosmic force fields present a serious ongoing threat to anyone who attempts to travel from place to place in the solar system. The largest of these objects likewise pose a threat to life on Earth, if they happen, as they certainly do on rare occasion, to collide with our planet at speeds of many miles per second. Local regions of space are so not empty that Earth, during its 30 km/s orbital journey around the Sun, plows into hundreds of tons of interplanetary debris per day, most of it no larger than a grain of sand. Nearly all of this matter burns in Earth's upper atmosphere, slamming into the air with so much energy that the incoming particles vaporize. Our frail species evolved beneath this protective blanket of air. Larger, golf ball-sized pieces of debris heat rapidly but unevenly, and often shatter into many smaller pieces before they vaporize. Still larger pieces singe their surfaces but otherwise make their way, at least in part, down to the ground. You might think that by now, after 4.6 billion trips around the Sun, Earth would have vacuumed up all possible debris in its orbital path. We have made progress in this direction. Things were once much worse. During the first half-billion years after the formation of the Sun and its planets, so much junk rained down on Earth that the impact energy generated a strongly heated atmosphere and a sterilized surface. In particular, one hunk of space junk was so substantial that it led to the formation of the Moon. The unexpected paucity of iron and other high-mass elements in the Moon, deduced from the lunar samples that the Apollo astronauts brought to Earth, indicates that the Moon most likely consists of matter spun from Earth's relatively iron-poor crust and mantle by a glancing collision with a wayward Mars-sized protoplanet. Some of the orbiting flotsam from this encounter coalesced to form our lovely, low-density satellite. Apart from this newsworthy event about 5 billion years ago, the period of heavy bombardment that Earth endured during its infancy was similar to that experienced by all the planets and other large objects in the solar system. They each sustained similar damage, with the airless, erosionless Moon and Mercury still preserving most of the craters produced during this period. In addition to the flotsam left from its epoch of formation, interplanetary space also contains rocks of all sizes thrust from Mars, the Moon, and probably Earth as their surfaces reeled from high-energy impacts. Computer studies of meteor strikes demonstrate conclusively that some surface rocks near ground zero will be thrown upward with enough speed to escape the object's gravitational tether. From discoveries of Martian meteorites on Earth, we can conclude that about 1,000 tons of rocks from Mars rain down on Earth each year. Perhaps the same amount of debris reaches Earth from the Moon. Thus we did not have to go to the Moon to retrieve Moon rocks. A few dozen of them have come to us on Earth, although they are not of our choosing, and we had not yet learned this fact during the Apollo program. If Mars ever harbored life, most likely billions of years ago when liquid water flowed freely on the Martian surface, then unsuspecting bacteria, stowed away in the nooks and crannies of the rock ejected from Mars, could have traveled to Earth for free. We already know that some varieties of bacteria can survive long periods of hibernation, as well as high doses of the solar ionizing radiation to which they would be exposed en route to Earth. The existence of spaceborne bacteria is neither a crazy idea nor pure science fiction. The concept even has an important sounding name, panspermia. If Mars spawned life before Earth did, and if simple life traveled from Mars on ejected rocks and seeded Earth, we may all be descendants of Martians. This fact might seem to obviate environmental concerns over astronauts who sneeze on the Martian surface, spreading their germs on the alien landscape. In reality, even if we are all Martian in origin, we would dearly like to trace life's trajectory from Mars to Earth, so these concerns retain vital importance. Most of the solar system's asteroids live and work in the main belt, a flattened region around the Sun between the orbits of Mars and Jupiter. By tradition, asteroid discoverers get to name their objects as they choose. Often pictured by artists as a cluttered region of rocks floating in the plane of the solar system, though in fact spread out over millions of miles at different distances from the Sun, the objects in the asteroid belt have a total mass less than 5% of the Moon's, which itself has barely more than 1% of Earth's mass. Sounds insignificant at first, but the asteroids quietly pose a long-term cosmic threat to our planet. Accumulated perturbations of their orbits continually create a deadly subset of asteroids, perhaps a few thousand in number, whose elongated paths carry them so close to the Sun that they intersect the orbit of Earth, creating the possibility of collision. A back-of-the-envelope calculation demonstrates that most of these Earth-crossing asteroids will strike Earth within a few 100 million years. The objects larger than about a mile across carry enough energy to destabilize Earth's ecosystem and to put most of Earth's land species at risk of extinction. That would be bad. Meanwhile, asteroids are not the only space objects that pose a risk to life on Earth. The Dutch astronomer Jan Oort first recognized that within the cold depths of interstellar space, much farther from the Sun than any planet, a host of frozen leftovers from the solar system's earliest stages of formation still orbit our star. This Oort cloud of trillions of comets extends to distances halfway to the closest stars, thousands of times larger than the size of the Sun's planetary system. Oort's Dutch-American contemporary Gerard Kuiper proposed that some of these frozen objects once formed part of the disk of material from which the planets formed, and now orbit the Sun at distances considerably greater than Neptune's but much less than those of the comets in the Oort cloud. Collectively, they compose what astronomers now call the Kuiper belt, a comet-strewn swath of circular real estate that begins just beyond the orbit of Neptune, includes Pluto, and extends several times as far again outward from Neptune as Neptune's distance from the Sun. The most distant known object in the Kuiper belt, named Sedna after an Inuit goddess, has 2/3 of Pluto's diameter. Without a nearby massive planet to perturb them, most of the Kuiper belt comets will maintain their orbits for billions of years. As in the asteroid belt, a subset of the Kuiper belt objects travel on eccentric orbits that cross the paths of other planets. The orbit of Pluto, which we may regard as an extremely large comet, as well as the orbits of an ensemble of Pluto's small siblings, called Plutinos, cross Neptune's path around the Sun. Other Kuiper belt objects, perturbed from their usual large orbits, occasionally plunge all the way into the inner solar system, crossing planetary orbits with abandon. This subset includes Halley, the most famous comet of them all. The Oort cloud is responsible for the long-period comets, those whose orbital periods far exceed a human lifetime. Unlike Kuiper belt comets, Oort cloud comets can rain down on the inner solar system from any angle and from any direction. The brightest comet of the past 3 decades, Comet Hyakutake, came from the Oort cloud, high above the plane of the solar system, and will not return to our vicinity anytime soon. If we had eyes that could see magnetic fields, Jupiter would look 10 times larger than the full moon in the sky. Spacecraft that visit Jupiter must be designed to remain unaffected by this powerful magnetism. As the English chemist and physicist Michael Faraday discovered in 1831, if you move a wire across a magnetic field, you will generate a voltage difference along the wire's length. For this reason, fast-moving metal space probes can have electrical currents induced within them. These currents interact with the local magnetic field in a way that retards the space probe's motion. This effect might explain the mysterious slowing down of the two Pioneer spacecraft as they exit the solar system. Both Pioneer 10 and Pioneer 11, launched during the 1970s, have not traveled quite so far into space as our dynamical models of their motions predict. After taking into account the effects of space dust encountered en route, along with recoils of the spacecraft arising from leaky fuel tanks, this concept of magnetic interaction, in this case with the Sun's magnetic field, may provide the best explanation for the slowdown of the Pioneers. Better detection methods and close-flying space probes have increased the number of known planetary moons so rapidly that counting moons has become almost obsolete. They seem to multiply as we speak. What matters now is whether any of these moons are fun places to visit or to study. By some measures, the solar system's moons are far more fascinating than the planets they orbit. Mars' two moons, Phobos and Deimos, appear in Jonathan Swift's classic Gulliver's Travels. Problem is, these two small moons were not discovered until more than 100 years later. Unless he was telepathic, Swift was presumably interpolating between Earth's single moon and Jupiter's 4. Earth's moon has about 1/400 of the Sun's diameter, but is also just about 1/400 as far from us as the Sun, giving the Sun and the Moon the same size on the sky, a coincidence not shared by any other planet-moon combination in the solar system. And one that grants Earthlings uniquely photogenic total solar eclipses. Earth has also locked onto the Moon's period of rotation, leaving the Moon's rotation period equal to its period of revolution around Earth. The capture has arisen from Earth's gravity, which exerts greater amounts of force on the denser parts of the Moon's interior and makes them always face toward Earth. Wherever and whenever this happens, as it does for Jupiter's 4 large moons, the locked moon shows only one face to its host planet. Jupiter's system of moons stunned astronomers when they obtained their first good look. Io, the large moon closest to Jupiter, has been tidally locked and structurally stressed by its gravitational interactions with Jupiter and with the other large moons. These interactions pump enough energy into Io to melt some of its rocky interior, making Io the most volcanically active object in the solar system. Jupiter's second large moon, Europa, has enough H2O that its internal heat, which arises from the same interactions that affect Io, has melted its subsurface ice, leaving a liquid ocean below an icy covering. Close-up images of the surface of Miranda, one of Uranus' moons, reveal badly mismatched patterns, as though the poor moon had been blown apart, and its pieces hastily glued back together. The origin of these exotic features remains a mystery, but may also be due to something simple, like the uneven upwelling of ice sheets. Pluto's lone moon, Charon, is so large and so close to Pluto that Pluto and Charon have tidally locked onto each other. Both objects have rotation periods equal to their periods of revolution around their common center of mass. By convention, astronomers name planets moons after significant Greek personalities in the life of the god whose name the planet bears, though they use the Roman counterpart's name for the planet itself. Because the classical gods led complicated social lives, no shortage of characters exists from which to draw names. Sir William Herschel was the first person to discover a planet beyond those easily visible to the naked eye, and he was ready to name this new planet after the king who might support his research. Had Sir William succeeded, the planet list would read Mercury, Venus, Earth, Mars, Jupiter, Saturn, and George. Fortunately, clearer heads prevailed, so that some years later the new planet received the classical name Uranus. But Herschel's original suggestion to name the planets moons after characters in William Shakespeare's plays and Alexander Pope's poem The Rape of the Lock remains the tradition to this day. Among Uranus' 17 moons we find Ariel, Cordelia, Desdemona, Juliet, Ophelia, Portia, Puck, and Umbriel, with 2 new moons, Caliban and Sycorax, discovered as recently as 1997. The Sun loses material from its surface at a rate of 200 million tons per second. The Sun loses this mass in the solar wind, which consists of high-energy charged particles. Traveling up to 1,000 miles per second, these particles stream through interplanetary space, where they are often deflected by planetary magnetic fields. In response, these particles spiral down toward a planet's north and south magnetic poles, colliding with atmospheric gas molecules to produce colorful auroral glows. The Hubble Space Telescope has spotted aurorae near the poles of both Saturn and Jupiter. On Earth, the aurorae borealis and australis serve as intermittent reminders of how sweet it is to have a protective atmosphere. Complete an orbit in about 90 minutes. Although no one can breathe at these altitudes, some atmospheric molecules remain, enough to drain orbital energy slowly from unsuspecting satellites. To combat this drag, satellites in low orbit require intermittent boosts, lest they fall back to Earth and burn up in the atmosphere. The most sensible way to define the edge of our atmosphere is to ask where the density of its gas molecules falls to the density of gas molecules in interplanetary space. With this definition, Earth's atmosphere extends thousands of miles into space. Orbiting high above this level, 23,000 miles above Earth's surface, are the communications satellites that carry news and views around Earth. At this special altitude, a satellite finds not only that Earth's atmosphere is irrelevant but also that its speed in orbit, thanks to the diminished pull from Earth at this greater distance from our planet, falls to the point that it takes 24 hours to complete each revolution around our planet. Moving in orbits that precisely match Earth's rotation rate, these satellites appear to hover above a single point on the equator, a fact that makes them ideal for relaying signals from one part of Earth's surface to another. Newton's law of gravity states that, although the gravity from a planet gets progressively weaker as you travel farther from it, no distance will reduce the force of gravity all the way to zero, and that an object with enormous mass can exert significant gravitational forces even at large distances. The planet Jupiter, with its mighty gravitational field, bats out of harm's way many comets that would otherwise wreak havoc on the inner solar system. By doing so, Jupiter acts as a gravitational shield for Earth, allowing long stretches of relative peace and quiet on Earth. Without Jupiter's protection, complex life would have a hard time growing interestingly complex, always living at the risk of extinction from a devastating impact. We have exploited the gravitational fields of planets for nearly every probe sent into space. The Cassini probe, for example, sent to Saturn for an encounter late in 2004, was launched from Earth on October 15, 1997, and was gravitationally assisted twice by Venus, once by Earth, and once by Jupiter. Like a multi-cushion billiard shot, trajectories from one planet to another using gravitational slingshots are common. Otherwise our tiny probes would not have enough speed and energy to reach their destinations. One of us is now accountable for a piece of the solar system's interplanetary debris. In November 2000, the main belt asteroid 1994 Ka, discovered by David Levy and Caroline Shoemaker, was named 13123 Tyson. A fun distinction, but there's no particular reason to get big-headed about it. As already noted, plenty of asteroids have familiar names such as Jody, Harriet, and Thomas. And plenty of other asteroids have names such as Merlin, James Bond, and Santa. Rising through 20,000, the count of asteroids with well-established orbits may soon challenge our capacity to name them. Whether or not that day arrives, there is curious comfort knowing that one's own chunk of cosmic debris is not alone, as it litters the space between the planets, joined by a long list of other chunks named for real and fictional people. When last checked, asteroid 13123 Tyson was not headed toward us, and so cannot be blamed for either ending or starting life on Earth. Worlds unnumbered. Planets beyond the solar system. Through worlds unnumbered though the God be known. 'Tis ours to trace him only in our own. He, who through vast immensity can pierce, see worlds on worlds compose one universe, observe how system into system runs what other planets circle other suns, what varied being peoples every star, may tell why he then has made us as we are. Alexander Pope, An Essay on Man. Nearly 5 centuries ago, Nicolaus Copernicus resurrected a hypothesis that the ancient Greek astronomer Aristarchus had first suggested. Far from occupying the center of the cosmos, said Copernicus, Earth belongs to the family of planets that orbit the Sun. Even though a majority of humans have yet to accept this fact, believing in their hearts that Earth remains immobile as the heavens turn around her, astronomers have long offered convincing arguments that Copernicus wrote the truth about the nature of our cosmic home. The conclusion that Earth ranks as just one of the Sun's planets immediately suggests that other planets fundamentally resemble our own, and that they may well possess their own inhabitants, endowed as we are with plans and dreams, work, play, and fantasy. For many centuries, astronomers who used telescopes to observe hundreds of thousands of individual stars lacked the ability to discern whether or not any of these stars have planets of their own. Their observations did reveal that our Sun ranks as an entirely representative star, whose near twins exist in great numbers throughout our Milky Way galaxy. If the Sun has a planetary family, so too might other stars, with their planets equally capable of giving life to creatures of all possible forms. Expressing this view in a manner that affronted papal authority brought Giordano Bruno to his death at the stake in 1600. Today, a tourist can pick his way through the crowds at the outdoor cafes in Rome's Campo di Fiori to reach Bruno's statue at its center, then pause for a moment to reflect on the power of ideas to triumph over those who would suppress them. As Bruno's fate helps to illustrate, imagining life on other worlds ranks among the most powerful ideas ever to enter human minds. Were this not so, Bruno would have lived to a riper age, and NASA would find itself shorter of funds. Thus speculation about life on other worlds has focused throughout history, as NASA's attention still does, on the planets that orbit the Sun. In our search for life beyond Earth, however, a great frost has appeared. None of the other worlds in our solar system seem particularly fit for life. And maintain itself, the fact remains that our initial explorations of Mars and Venus, as well as of Jupiter and its large moons, have failed to produce any convincing signs of life. To the contrary, we have found a great deal of evidence for conditions extremely hostile to life as we know it. Much more searching remains to be done, and fortunately continues to be underway, especially in the hunt for life on Mars. Nevertheless, the verdict on extraterrestrial life in the solar system shows enough likelihood of proving negative that supple minds now usually look beyond our cosmic neighborhood, to the vast array of possible worlds that orbit stars other than our Sun. Until 1995, speculation about planets around other stars could proceed almost entirely unfettered by facts. With the exception of a few pieces of Earth-sized debris in orbit around the remnants of exploded stars, which almost certainly formed after the supernova explosion and barely qualified as planets, astrophysicists had never found a single exosolar planet, a world orbiting a star other than the Sun. At the end of that year came the dramatic announcement of the first such discovery, then, a few months later, came 4 more, and then, with the floodgates open, finding new worlds proceeded ever more swiftly. Today, we know of far more exosolar planets around other stars than of the now familiar worlds that orbit the Sun, a tally that exceeds 100 and is almost certain to keep growing for years to come. To describe these newfound worlds, and analyze the implications of their existence in the search for extraterrestrial life, we must confront a single hard-to-believe fact, although astrophysicists assert that they not only know that these planets exist but have also deduced their masses. Their distances from their parent stars, the times that the planets take to complete their orbits, and even the shapes of those orbits, no one has ever seen or photographed a single one of these exosolar planets. How can anybody deduce so much about planets they have never seen? The answer lies in detective work familiar to those who study starlight. By separating that light into its spectrum of colors, and by comparing those spectra among thousands of stars, those who specialize in observing starlight can recognize different types of stars purely by the ratios of the intensities of the different colors that appear in stellar spectra. Once upon a time, these astrophysicists photographed the stars' spectra, but today they use sensitive devices that register digitally how much starlight of each particular color reaches us on Earth. Though the stars are many trillions of miles from us, their fundamental natures have become an open book. Astrophysicists can now easily determine, purely by measuring the spectrum of the colors of starlight, which stars most closely resemble the Sun, which are somewhat hotter and more luminous, and which are cooler and intrinsically fainter than our star. But they can also do more. Having grown familiar with the distribution of colors in the spectra of various types of stars, astrophysicists can quickly identify a familiar pattern in the star's spectrum, which typically shows the partial or total absence of light at particular colors. They often recognize such a pattern, but find that all the colors that form it have been slightly shifted toward either the red or the violet end of the spectrum, so that all the familiar guideposts are now either somewhat redder or somewhat more violet than the norm. Scientists characterize these colors by their wavelengths, which measure the separation between successive wave crests in the vibrating light waves. Because they correspond with the colors that our eyes and brains perceive, specifying exact wavelengths simply names colors more precisely than we do in normal speech. When astrophysicists spot a familiar pattern in the intensity of light measured for thousands of different colors, but find that all the wavelengths in the pattern are 1% longer than usual, they conclude that the star's colors have changed as the result of the Doppler effect, which describes what happens when we observe an object either approaching us or receding from us. If, for example, an object moves toward us, or we move toward it, we find that all the wavelengths of the light that we detect are shorter than those we measure from an identical object at rest with respect to ourselves. If the object recedes from us, or we recede from it, we find all the wavelengths to be longer than those from an object at rest. The deviation from the at-rest situation depends on the relative velocity between the light source and those who observe it. For speeds much less than the speed of light, the fractional change in all the wavelengths of light, called the Doppler shift, equals the ratio of the speed of approach or recession to the speed of light. During the 1990s, two teams of astronomers, one in the United States and one centered in Switzerland, devoted themselves to increasing the precision with which they could measure the Doppler shifts of starlight. They did so not simply because scientists always prefer to make more accurate measurements, but because they had a straightforward goal: to detect the existence of planets by studying the light from stars. Why this roundabout approach to the detection of exosolar planets? Because for now this method offers the only effective way to discover them. If our solar system offers any guide to the distances at which planets orbit stars, we must conclude that these distances amount to only a tiny fraction of the distances between stars. The Sun's closest neighbor stars are about 500,000 times farther from us than the distance between the Sun and its innermost planet, Mercury. Even Pluto's distance from the Sun is less than 1/5000th of the distance to Alpha Centauri, our closest star system. These astronomically minuscule separations between the stars and their planets, combined with the faintness with which a planet reflects light from its star, make it nearly impossible for us to actually see any planets beyond the solar system. Imagine, for example, an astrophysicist on a planet around one of the Alpha Centauri stars who turns her telescope toward the Sun and attempts to spot Jupiter, the Sun's largest planet. The Sun-Jupiter distance amounts to only 1/50,000th of the distance to the Sun, and Jupiter shines with just 1/1000th of the Sun's intensity. Astrophysicists like to compare this to the problem of seeing a firefly next to a searchlight's glare. We may do it someday, but for now the quest to observe exosolar planets directly lies beyond our technological capabilities. The Doppler effect offers another approach. If we study the star closely, we can carefully measure any changes that appear in the Doppler shift of the light from that star. These changes must arise from changes in the speed with which the star is either approaching us or receding from us. If the changes prove to be cyclical, that is, if their amounts rise to a maximum, fall to a minimum, rise to the same maximum again, and repeat this cycle over the same intervals of time, then the entirely reasonable conclusion follows that the star must be moving in an orbit that takes it around and around some point in space. What could make a star dance like that? Only the gravitational force from another object, so far as we know. No doubt that planets, by definition, have masses much less than the mass of a star, so they exert only modest amounts of gravitational force. When they pull on a nearby star that possesses far more mass than they do, they produce only small changes in the star's velocity. Jupiter, for example, changes the Sun's velocity by about 40 feet per second, slightly more than the speed of a world-class sprinter. As Jupiter performs its 12-year orbit around the Sun, an observer located along the plane of this orbit would measure Doppler shifts in the Sun's light. These Doppler shifts would demonstrate that at a particular time, the Sun's velocity with respect to the observer would rise 40 feet per second above its average value. 6 years later, the same observer would find that the sun's velocity is 40 feet per second less than average. During the interim, this relative velocity would shift smoothly between its two extreme values. After a few decades of observing this repetitive cycle, the observer would justifiably conclude that the sun has a planet moving in a 12-year orbit that causes the sun to perform its own orbit, producing the velocity changes that arise naturally from this motion. The size of the sun's orbit, in comparison to the size of Jupiter's, exactly equals the inverse of the ratio of the two objects' masses. Since the sun has 1,000 times Jupiter's mass, Jupiter's orbit around their mutual center of gravity is 1,000 times larger than the sun's, testimony to the fact that the sun is 1,000 times more difficult to budge than Jupiter. Of course, the sun has many planets, each of which simultaneously pulls on the sun with its own gravitational force. The sun's net motion therefore amounts to a superposition of orbital dances, each with a different cyclical period of repetition. Because Jupiter, the sun's largest and most massive planet, exerts the greatest amount of gravitational force on the sun, the dance imposed by Jupiter dominates this complex pattern. When astrophysicists sought to detect exosolar planets by watching stars dance, they knew that to find a planet roughly similar to Jupiter, orbiting its star at a distance comparable to Jupiter's distance from the sun, they would have to measure Doppler shifts with an accuracy sufficient to reveal velocity changes of approximately 40 feet per second. On Earth this sounds like a significant speed. But in astronomical terms, we are talking about less than 1/millionth of the speed of light, and about 1,000th of the typical speed with which stars happen to be moving toward us or away from us. Thus, to detect the Doppler shift produced by a change in velocity equal to 1/millionth of the speed of light, astrophysicists must measure changes in wavelength, that is, in star colors, of 1 part in a million. These precision measurements yielded more than the detection of planets. First of all, because the detection scheme lies in finding a cyclical repetition in the changes of a star's velocity, the length of each of these cycles directly measures the orbital period of the planet responsible for it. If the star dances with a particular cycle of repetition, the planet likewise must be dancing with an identical period of motion, though in a much larger orbit. This orbital period in turn reveals the distance of the planet from the star. Isaac Newton long ago proved that an object orbiting a star will complete each orbit more rapidly when closer to the star, more slowly when farther away. Each orbital period corresponds to a particular value of the average distance between the star and the orbiting object. In the solar system, for instance, a 1-year orbital period implies a distance equal to the Earth-Sun distance, whereas a 12-year period implies a distance 5.2 times larger, the size of Jupiter's orbit. So the research team could announce not only that they had found a planet but also that they knew both the planet's orbital period and its average distance from its star. They could deduce still more about the planet. Moving at a particular distance from its star, a planet's gravity will pull on the star with a force that depends on the planet's mass. More massive planets exert greater force, and these forces make the star dance more rapidly. Once they knew the planet-star distances, the team could then include the masses of the planets in the list of planetary characteristics that they had determined through careful observation and deduction. This deduction of a planet's mass by observing the star's dance comes with a disclaimer. Astronomers have no way to tell whether they are studying a dancing star from a direction that happens to coincide exactly with the plane of the planet's orbit, or from a direction directly above the plane of the orbit, or from a direction neither exactly along the plane nor directly perpendicular to it. The plane of the planet's orbit around the star coincides with the plane of the star's motion in response to the planet's gravity. We therefore observe the full orbital speeds only if our line of sight to the star happens to be the same as the plane of the planet's orbit around the star. To imagine a loosely analogous situation, put yourself at a baseball game, able to measure the speed of the pitched ball as it comes toward you or moves away, but not the speed with which the ball crosses your field of vision. If you are a talent scout, the best place for you to sit is behind home plate, in direct line with the baseball's motion. But if you observe the game from the first or third baselines, the ball thrown by the pitcher will, for the most part, neither approach you nor recede from you, so your measurement of the ball's speed along your line of sight will be nearly zero. Because the Doppler effect reveals only the speed with which a star moves toward us or away from us, but not how rapidly the star crosses our line of sight, we usually cannot tell how nearly our line of sight to the star lies in the plane of the star's orbit. This fact implies that the masses that we deduce for exosolar planets are all minimum masses. They will prove to be the planet's actual masses only in those cases when we do observe the star along its orbital plane. On the average, the actual mass of an exosolar planet equals twice the minimum mass deduced from observing the star's motions, but we have no way to know which exosolar planet masses lie above this average ratio, and which below. In addition to deducing the planet's orbital period and orbital size, as well as the planet's minimum mass, astrophysicists who study star dances by the Doppler effect have one more success: they can determine the shape of the planet's orbit. Some of these orbits, like those of Venus and Neptune around the Sun, have an almost perfect circularity, but others, like the orbits of Mercury, Mars, and Pluto, have significant elongation, with the planet traveling much closer to the Sun at some points along its orbit than at others. Because a planet moves more rapidly when it is closer to its star, the star changes its velocity more rapidly at those times. If astronomers observe a star that changes its velocity at a constant rate throughout its cyclical period, they conclude that these changes arise from a planet moving in a circular orbit. If, on the other hand, they find that the changes sometimes occur more rapidly and sometimes more slowly, they deduce that the planet has a non-circular orbit, and can find the amount of the orbital elongation, the amount by which the orbit deviates from circularity, by measuring the different rates at which the star changes its velocity throughout the orbital cycle. Thus, in a triumph of accurate observations coupled with their powers of deduction, astrophysicists who study exosolar planets can provide 4 key properties of any planet that they find: the planet's orbital period, its average distance from its star, its minimum mass, and its orbital elongation. Astrophysicists achieve all this by capturing the colors of light from stars that lie hundreds of trillions of miles from the solar system, and by measuring those changes with a precision better than 1 part in a million, a high point in our attempts to probe the heavens in a search for Earth's cousins. Only one problem remains. Many of the exosolar planets discovered during the past decade orbit their stars at distances much smaller than any of the distances between the Sun to its planets. This issue looms larger because all the exosolar planets so far detected have masses comparable to that of Jupiter, a giant planet that orbits the Sun at more than 5 times the Earth-Sun distance. Let us take a moment to examine the facts, before we admire the astrophysicists' explanations of how these planets may have come to occupy orbits so much smaller than those familiar to us in our own planetary system. Whenever we use the star dance method to search for planets around other stars, we must remain aware of the biases built into this method. First, planets close to their stars take much less time to orbit than do planets far from their stars. Since astrophysicists have limited amounts of time with which to observe the universe, they will naturally discover planets moving in, for example, 6-month periods far more quickly than they can detect planets that take a dozen years for each orbit. In both cases, the astrophysicists must wait through at least a couple of orbits to be certain that they have detected a repeatable pattern of the changes in the star's velocities. To find planets with orbital periods comparable to Jupiter's 12 years could therefore consume much of an individual's professional career. Second, a planet will exert more gravitational force on its host star when close rather than when far. These greater forces make the star dance more rapidly, producing larger Doppler shifts in their spectra. Since we can detect larger shifts more easily than smaller ones, the closer-in planets attract more attention, and do so more rapidly, than the farther-out planets do. At all distances, however, an exosolar planet must have a mass roughly comparable to Jupiter's to be detected by the Doppler shift method. Planets with significantly less mass cannot make their stars dance with a speed that rises above the threshold of detectability by today's technology. In hindsight, then, no surprise should have accompanied the news that the first exosolar planets to be discovered all have masses comparable to Jupiter's, and all orbit close to their stars. The surprise lay in just how close many of these planets turned out to be, so close that they take not several months or years to complete each orbit, as the Sun's planets do, but only a few days. Astrophysicists have now found more than a dozen planets that complete each orbit in less than a week, with the record holder sweeping out each orbit in just over 2.5 days. This planet, which orbits the Sun-like star known as HD 73256, has a mass at least 1.9 times Jupiter's mass, and moves in a slightly elongated orbit at an average distance from its star equal to only 3.7% of the Earth-Sun distance. In other words, this giant planet possesses more than 600 times Earth's mass at a distance from its star less than 1/10 that of Mercury. Mercury consists of rock and metal, baked to temperatures of many hundred degrees on the side that happens to face the Sun. In contrast, Jupiter and the Sun's other giant planets are enormous balls of gas, surrounding solid cores that include only a few percent of each planet's mass. All theories of planet formation imply that a planet with a mass comparable to Jupiter's cannot be solid, like Mercury, Venus, and Earth, because the primordial cloud that formed planets contained too little of the stuff that can solidify to make a planet with more than a few dozen times the mass of Earth. The conclusion follows, as one more step in the great detective story that has given us exosolar planets, that all exosolar planets so far discovered must likewise be great balls of gas. Two questions immediately arise from this startling conclusion. How did these Jupiter-like planets ever come to orbit so close to their stars, and why doesn't their gas quickly evaporate under the intense heat? The second question has a relatively easy answer. The planet's enormous masses can retain even light gases heated to temperatures of hundreds of degrees, simply because the planet's gravitational forces can overcome the tendency of the atoms and molecules in the gas to escape into space. In the most extreme cases, however, this contest tips only narrowly in favor of gravity, and the planets lie just outside the distance at which their stars' heat would indeed evaporate their gases. The first question, of how giant planets came to orbit so close to Sun-like stars, brings us to the fundamental issue of how planets formed. As we have seen in Chapter 11, theorists have worked hard to achieve some understanding of the planet formation process in our solar system. They conclude that the Sun's planets accumulated themselves into being, growing from smaller clumps of matter into larger ones within a pancake-shaped cloud of gas and dust. Within this flattened, rotating mass of matter that surrounded the Sun, individual concentrations of matter formed, first at random, but then, because they had a density greater than average, by winning the gravitational tug-of-war among particles. In the final stages of this process, Earth and the other solid planets survived an intense bombardment from the last of the giant chunks of material. As this agglutinative process unfolded, the Sun began to shine, evaporating the lightest elements, such as hydrogen and helium, from its immediate neighborhood, and leaving its 4 inner planets composed almost entirely of heavier elements such as carbon, oxygen, silicon, aluminum, and iron. In contrast, each of the clumps of matter that formed at 5 to 30 times Earth's distance from the Sun remained sufficiently cool to retain much of the hydrogen and helium in its vicinity. Because these two lightest elements are also the most abundant, this retentive ability produced 4 giant planets, each with many times Earth's mass. Pluto belongs neither to the class of rocky, inner planets nor to the group of outer gas giant planets. Instead, Pluto, still uninspected by spacecraft from Earth, resembles a giant comet, made of a mixture of rock and ice. Comets, which typically have diameters of 5 to 50 miles rather than Pluto's 2,000 miles, rank among the first sizable clumps of matter to form within the early solar system. They are rivaled in age by the oldest meteorites, which are fragments of rock, metal, or rock and metal mixtures that happen to have struck Earth's surface and to have been recognized by those who know how to tell a meteorite from a garden-variety rock. Thus the planets built themselves from matter much like that in comets and meteorites, with the giant planets using their solid cores to attract and retain a much larger amount of gas. Radioactive dating of the minerals in meteorites have shown that the oldest of them have ages of 4.55 billion years, significantly greater than the oldest rocks found on the Moon or on Earth. The birth of the solar system, which therefore occurred about 4.55 billion BC, quite naturally led to the segregation of planetary worlds into 2 groups, the relatively small, solid inner planets and the much larger, more massive, mainly gaseous giant planets. The 4 inner planets orbit the Sun at distances of 0.37 to 1.52 times the Earth-Sun distance, while the 4 giants remain at the much greater distances, ranging from 5.2 to 30 times the Earth-Sun distance, which allowed them to be giants. This description of how the Sun's planets formed makes such good sense that it almost seems a shame that we have now found so many examples of objects with masses similar to Jupiter's, moving in orbit around their stars at distances much less than Mercury's distance from the Sun. Indeed, because the first exosolar planets to be discovered all had such small distances from their stars, for a time it appeared as though our solar system might prove the exception, rather than the model of planetary systems. As theorists had implicitly assumed in the days when they had nothing else on which to base their conclusions. Understanding the bias imposed by the relative ease of discovering close-in planets gave them some reassurance, and before long they had observed for sufficiently long times, and with sufficient accuracy, to detect gas giant planets at much greater distances from their stars. Today, the list of exosolar planets, ordered by distance from the star to the planet, begins with the entry described above, of a planet that takes only 2.5 days to perform each orbit, and extends, through well over 100 entries, to the star 55 Cancri, where a planet with at least 4 times the mass of Jupiter takes 13.7 years for each orbit. Astrophysicists can calculate from the orbital period that this planet has a distance from its star equal to 5.9 times the Sun-Earth distance, or 1.14 times the distance from the Sun to Jupiter. The planet ranks as the first to be found with a distance from its star greater than the Sun-Jupiter distance, and therefore seems to provide a planetary system roughly comparable to our solar system, at least so far as the star and its largest planet are concerned. However, this is not quite so. The planet that orbits 55 Cancri at 5.9 times the Earth-Sun distance represents not the first but the third to be discovered in orbit around this star. By now, astronomers have accumulated sufficient data, and have grown so skilled at interpreting their Doppler shift observations, that they can disentangle the complex star dance produced by 2 or more planets. Each of these planets attempts to impose a dance in its own rhythm, with a repetitive period equal to the span of the planet's orbit around the star. By observing for a sufficiently long time, and by employing computer programs that fear no calculation, planet hunters can tease from coming-led dances the basic steps induced by each orbiting world. In the case of 55 Cancri, a modest star visible in the constellation called the Crab, they had already found 2 closer-in planets, with orbital periods of 42 days and 89 days and minimum masses of 0.84 and 0.21 Jupiter masses, respectively. The planet with a minimum mass equal to only 0.21 Jupiter masses ranks among the least massive yet detected, but the record low mass for an exosolar planet has now fallen to 35 Earth masses, still so many times greater than Earth's that we should not hold our breath in anticipation that astronomers will soon find Earth's cousins. Circle it as we may, we cannot avoid the problem, evident from the orbits of the planets around 55 Cancri, of explaining why and how many exosolar planets, with masses much like Jupiter's, orbit their stars at stunningly small distances. No planet with a Jupiter-like mass can form, experts will tell you, much closer to a Sun-like star than 3 to 4 times the Earth-Sun distance. If we assume that exosolar planets obey this dictum, they must have somehow moved to much smaller distances after. 1. What made these planets move into smaller orbits after they had formed? 2. What stopped them from moving all the way into their stars and perishing? 3. Why did this occur in many other planetary systems, but not in our solar system? These questions have answers, supplied by fertile minds once they had been properly stimulated by the discovery of exosolar planets. We may summarize the scenario now favored by experts as follows. 1. Planetary migration occurred because significant amounts of material left over from the formation process continued to orbit the star within the orbits of the new-formed giant planets. This material gets systematically flung by the big planet's gravity to outer orbits, which in turn forces the big planet to creep inward. 2. When the planets had approached much closer to their stars than their points of origin, the tidal forces from the star locked the planet into place. These forces, comparable to the tidal forces from the Sun and Moon that raise tides in Earth's oceans, forced the planet's rotational periods to equal their orbital periods, as happened to the Moon from Earth's tidal forces. They also prevented any further approach of the planet to the star, for reasons that require sufficient involvement with celestial mechanics to merit passing over here. 3. Presumably the luck of the draw determined which planetary systems formed with large amounts of debris, capable of inducing planetary migration, and which, like our own, had relatively little debris, so the planets remained at the distances at which they had formed. In the case of the planets around 55 Cancri, it is possible that all three migrated significantly inward, with the outermost planet having formed at several times its current distance from the star. Or it may be that the details of how much debris lived inside the planet's orbit, and how much outside, caused significant migration of the two inner planets, while the third has remained in its original path. Some work remains to be done, to put things politely, before astrophysicists can proclaim they have explained how planetary systems form around stars. Meanwhile, those who hunt for exosolar planets continue to pursue their dream of finding Earth's twin, a planet similar to Earth in its size, mass, and orbital distance from its parent star. When and if they find such a planet, they hope to examine it, even from a distance of dozens of light years, with sufficient precision to determine whether the planet possesses an atmosphere and oceans similar to Earth's, and perhaps whether life exists upon that planet like our own. In pursuit of this dream, astrophysicists know that they need instruments orbiting above our atmosphere, whose blurring effects prevent us from making extremely precise measurements. One experiment, NASA's Kepler mission, aims at observing hundreds of thousands of nearby stars, seeking the tiny diminution in starlight caused by the motion of an Earth-sized planet across our line of sight to a star. This approach can succeed only for the small fraction of situations in which our view lies almost exactly along the planet's orbital plane, but for those cases, the interval between planetary transits equals the planet's orbital period, which in turn specifies the planet-star distance. And the amount of starlight diminution reveals the size of the planet. However, if we hope to find out more than the planet's bare physical characteristics, we must study the planet by direct imaging and analysis of the spectrum of the light that the planet reflects into space. NASA and ESA, the European Space Agency, have programs underway to achieve this goal within 2 decades. To see another Earth-like planet, even as a pale blue dot close to a far brighter star, could inspire another generation of poets, physicists, and politicians. To analyze the planet's reflected light, and thus to determine whether or not the planet's atmosphere contains oxygen or oxygen plus methane, would mark the sort of accomplishment that the bards once sang. Elevating mere mortals into heroes for the ages, leaving us face to face with something commensurate with man's capacity to wonder. For those who dream of finding life elsewhere in the universe, our final section awaits. The Origin of Life. Chapter 14. Life in the Universe. Our survey of origins brings us, as we knew it would, to the most intimate and arguably the greatest mystery of all, the origin of life, and in particular of forms of life with which we may someday communicate. For centuries, humans have wondered how we might find other intelligent beings in the cosmos, and with whom we might enjoy at least a modest conversation before we pass into history. The crucial clues for resolving this puzzle may appear in the cosmic blueprint of our own beginnings, which includes Earth's origin within the Sun's family of planets, the origin of the stars that provide energy for life, the origin of structure in the universe, and the origin and evolution of the universe itself. If we could only read this blueprint in detail, it could direct us from the largest to the smallest astronomical situations, from the unbounded cosmos to individual locations where different types of life flourish and evolve. If we could compare the diverse forms of life that arose under various circumstances, we could perceive the rules of life's beginnings, both in general terms and in particular cosmic situations. Today, we know of only one form of life, life on Earth, all of which shares a common origin and uses DNA molecules as the fundamental means of reproducing itself. This fact deprives us of multiple examples of life, relegating to the future a general survey of life in the cosmos, unachievable until the day we begin to discover forms of life beyond our planet. Things could be worse. We do know a great deal about life's history on our planet, and must build on this knowledge to derive basic principles about life throughout the universe. To the extent that we can rely on these principles, they will tell us when and where the universe provides, or has provided, the basic requirements for life. In all our attempts to imagine life elsewhere, we must resist falling into the trap of anthropomorphic thinking, our natural tendency to imagine that extraterrestrial forms of life must be much like our own. This entirely human attitude, which arises from our evolutionary and personal experiences here on Earth, restricts our imagination when we attempt to conceive how different life on other worlds may be. Only biologists familiar with the amazing variety and appearance of different forms of life on Earth can confidently extrapolate what extraterrestrial creatures might look like. Their strangeness almost certainly lies beyond the imaginative powers of ordinary humans. Someday, perhaps next year, perhaps